let's just do a little bit of review from general chemistry again that will help us in describing how reactions proceed. So let's start with equilibrium. Reactions, remember, can move either forward or reverse to reach equilibrium. Okay? You can write a reaction really however you want, but in real life it will go towards whichever side gets it to equilibrium. So typically in organic chemistry, we want the products to be favored. We're going to write a reaction where it's reactants making products. Okay? It's not going to be very useful to us if just the reactants are favored. We'll just have reactants that will just sit there and not form any new products. Okay? We want products to be favored. So what does that mean about equilibrium? Well, in general chemistry, the equilibrium constant, and we call it KEQ here. You called it Kc or Kp in general chemistry. KEQ is just in general, and then it's never confused with any of the other dozens of Ks that are used in chemistry. So KEQ, ratio of product concentrations over reactant concentrations, and if you have balancing coefficients, the concentrations get raised to those powers in the equilibrium constant expression. Okay, so product concentrations raised to their coefficients over reactant concentrations raised to their coefficients. Okay, so for the reaction we just studied, ethylene and HBr, it turns out the equilibrium constant for that is very high, 7 times 10 to the 7. Okay? That means the concentration of the product, okay, the CH3CH2Br, will be much, much larger than the concentration of reactants when this reaction is allowed to reach equilibrium, right? In general, if you have an equilibrium constant over 1,000, that's our optimal condition in organic chemistry. K over 1,000 means the reaction essentially goes to completion. We'll have 1,000 times the product concentration as the reactant concentration. And if that's the case, when it's 1,000 times like that, we usually will not even be able to detect the presence of starting material. Okay? When it's, 1% or 0.5% of starting material or something, we can detect that. You do gas chromatography in lab, where you can get down to 0.1% in analyzing a product mixture, right? But K over 1,000, you'll have a real hard time finding any unreacted starting material in there. If you're doing gas chromatography or something, it'll be just a little blip on your chromatogram. Okay? So this is an optimal condition for us from an equilibrium sense. Okay? Equilibrium is not the entire story, as we'll see in a moment, but it is important. The reason, though, that this equilibrium constant is what it is all comes from the energetics of the reactants and the products. So let's look at that. Free energy and equilibrium. In order for a reaction to proceed to completion, the products must be lower in potential energy than the reactants. So this is the common thing of potential energy that you hear over and over again. Okay? We go from states of high potential energy to states of low potential energy, and that happens spontaneously. The example we always use is of positional potential energy. If you drop something from a height, right, when you're holding something up high, it has a lot of potential energy, and you let it go, it drops down to the ground where it has much less potential energy. So reactive high energy molecules, they lose energy in order to become more stable low energy molecules. That's what will happen spontaneously in a chemical reaction. Now, depending on whether those low energy molecules happen to be your reactants or your products, that's what determines if your reaction is going to go or not. If you have two reactants that are already more stable than the products, right, they already have lower potential energy than the products, then you're going to have a real hard time getting products out of that. Okay? So for organic chemistry, that potential energy that we talk about is Gibbs free energy. And that was something that was introduced to you in general chemistry, should have been. Gibbs free energy, delta G, Gibbs free energy change, is the change in potential energy over the course of a reaction. So in order to have an equilibrium constant greater than 1. So in order to favor your products, delta G must be negative. Why is that? The system must be releasing energy in order to become more stable. If we go from high energy reactants to low energy products, okay, that's going the normal direction of spontaneous change. Okay? That's a spontaneous process. That will favor our products. That'll give us what we expect. But in order for us to have an equilibrium constant less than 1, which means our reactants are favored, the delta G must be positive. In other words, the system would have to gain potential energy and it would have to become less stable in order to proceed as written. So if I wanted to make a less stable product, there are some ways of doing it by constantly feeding energy into the system. And if you can then isolate a product, you can then take a product out of it without it reacting back again. That might be one way of doing it, but typically that's a much more difficult situation to be in than if your products are more stable energetically than your reactants are. Okay? And that will be the typical case. When we draw two reactants with a forward arrow making two products, or whatever reactants making products that way, we're going to assume that's a spontaneous process. We're going to assume the products are lower in energy and more stable than the reactants. The book and some other places use the terms endergonic and exergonic as ways to describe reactions. A spontaneous process, exergonic. A non-spontaneous process, endergonic. I don't know, I guess I don't see those terms being used too much in chemistry, although they do like to use them in biology. So a lot of you are taking a biochemistry class after this, or after a year of organic chemistry anyway, so they like to hang on to those terms. So keep those in your head. You won't hear me using those an awful lot. I just like saying spontaneous. I think that makes a lot more sense. So spontaneous process is one that will occur, right, if the system is allowed to reach equilibrium. Right? It'll occur as written in the forward direction. So what is it that determines the free energy change? What is it that determines whether the products will be lower in potential energy or higher in potential energy than the reactants? Well, there are two energetic terms that influence delta G. You learned this equation in general chemistry. I've told my general chemistry students sometimes that of the couple of important things that I took from general chemistry to go on to graduate school, delta G equals delta H minus T delta S is one of them. Delta G 0 equals minus RT natural log of K is the other one. Okay? That's what relates equilibrium constant with delta G. So we talked about that before. But delta H and delta S are the energetic terms that actually determine whether or not something will be higher or lower in potential energy. So enthalpy is delta H. For organic chemistry, enthalpy is just related to the strength of bonds that are formed and that are broken. Okay? There are some bonds that are stronger and some that are weaker than others. Well, I'll give you a page of those in just a moment. A favorable enthalpy change, an enthalpy change that will favor a spontaneous reaction, will have stronger bonds in the product. We'll talk more about that later, but it's going to be favorable for us to form stronger bonds. If we have reactants with weak bonds, they will tend to form products with stronger bonds in a spontaneous process. But that's not all. There's also entropy change. And it's really pretty simple to look at entropy change in organic reactions. Just think of it as freedom of motion. Think of it as dispersion of energy. We've really tried in recent years to get away from this disorder and randomness definition, although it's pretty harmless to think about that in organic chemistry if you want to. But if we look at an elimination, okay, A makes B plus C. One molecule becomes two molecules. That's a favorable entropy change. the energy that was contained within this one reactant here is now more dispersed into twice as many product molecules. Okay? That's favorable in the normal flow of entropy in the universe. Addition is the opposite, though. You take two molecules, you combine them together to make one. What was more dispersed energy now gets more concentrated into half as many molecules. That's an unfavorable entropy change. Addition reactions really can only be spontaneous if their enthalpy change is such that it can override the entropy. Okay? It's sort of a penalty in combining molecules together in terms of entropy. So they better be making much stronger bonds when you're combining them, okay, in order for that to work. Similarly, if you're making weaker bonds, there had better be a really good entropy change. So if you're making weaker bonds, you better be making a lot of molecules. You better be spreading that energy out quite a bit. So these two terms act together in this equation. Delta G equals delta H minus T delta S. We do not need to calculate that anymore in this class, but understand that both enthalpy and entropy work together in order to make a reaction spontaneous. And if you have something unfavorable in one, the other needs to override that in order to have a spontaneous reaction.